Okay, welcome back to the afternoon session. So we are starting with Spotlight Talk. So this should be really interesting because it's very recent work that people have submitted to the workshop. People, this is also where you can dive deeper later in the afternoon coffee break, because you can discuss the work further with them at their poster. And then we have three more talks, or four more talks really. Anyway, five more talks. I'm sorry, I'm just checking the coffee break in between, but really we have a number of more talks, really exciting ones. I think they will broaden our perspective in addition to what we already heard today in the morning. And at the end, we will have a panel session again. And I think this should also be really interesting for you to interact with the speakers. So let's get started with the spotlight talks.
Hi, everyone. I'm Suvir from Stanford. This is joint work with David Yuan, Kaylee Burns, Sajid Islam, Tony Zhao, Chelsea Finn, and Dorsa Sadiq. So we're presenting RoboCrowd, a framework for crowdsourcing robot demonstration data. So the motivation for this, as we've seen, end-to-end data-driven methods are really promising and powerful, in narrow settings, as long as we have the data, as long as we have abundant data, but we don't quite have abundant data yet. And one of the reasons why is that the human effort required for collecting data for imitation learning is burdensome to collect. Right. And one of the sort of underlying reasons for this is we don't have mechanisms to sort of distribute data collection between, researchers and dedicated robot operators and non-experts, more broad set of users. So in this work, we look at sort of ways that we can transform the process of robot data collection into something that's a bit more distributed over many different users through crowdsourcing and incentive design. So to do this, we developed RoboCrowd, a framework for incentivizing crowdsourced demonstration collection in the real world. And so we center five key properties: being publicly accessible to non-experts, capable hardware, intuitive operation to non-experts, safety, and gamification. And so I'll give a quick overview of the system. So we build the system upon Aloha, a low-cost system for bimanual teleoperation, and we do a variety of hardware and software enhancements to make the system intuitive and safe for non-experts. And we also develop a interface to onboard non-expert users to how to operate the system, including tutorials and sort of a gamified interface where people can select different tasks they can do in various scenes. And so our key idea is with this system to sort of align incentives to shape the crowdsourced interactions that people might have with the robot into useful data for imitation learning. So for example, here, a user might grab a candy out of a bin, right? So some sort of semi-precise picking task from a bin, and they're not really intending to provide data. They're just trying to get a candy out of a bin. But in the process, they're adding to this sort of crowdsourced data set for bin picking that we would create. So this is a simple example, but we look at other incentives as well. For example, intrinsic motivation for people just having fun interacting with the robot, and an idea of social comparison where people kind of compete to try to do better on different tasks. So we actually deployed this for a couple of weeks in a cafe at Stanford, where people could just kind of organically come up to the system and play with it. And we collected around 800 interaction episodes from over 200 users in this sort of self-organized gamified experience. And we set up some different scenes to sort of experimentally test some various incentive mechanisms in shaping the types of data that people could give with the system. So I'll give a quick overview of our results. So here's a scene where we collect data for users sort of attempting different bin picking tasks, one with a Hi-Chew candy and one with a Tootsie Roll candy. And it turns out people prefer Hi-Chew, so more of their data was focused on that task. So this is kind of like a crisp example to show that how these different material incentives can shape user interaction. But something interesting we see is that users actually focus a lot on play data. So they try to construct their own tasks that are harder than the ones we put out. And this is something consistently we see when we construct other tasks as well, like this this kind of complex bimanual task of ejecting jelly beans from a dispenser that people try to attempt. And we also sort of see this as well, where when we control for different material incentives and see, we put candies inside of a Ziploc, and people tend to go for the candies inside the Ziploc that require unzipping the Ziploc instead of just like grabbing the candy out of a bin, which points to this idea of like intrinsic motivation as a useful incentive for shaping these interactions. We also add this like leaderboard page for social comparison, and find that people who tend to be more competitive and look at the leaderboard actually give slightly more data and slightly higher quality data as well. And we also have some preliminary results on using the crowdsourced data for pre-training robot policies. So we see some signs of life here, but I will point out that like some of the crowdsourced data is pretty, low quality and noisy. So this presents like definitely a research challenge in figuring out how to leverage the most from this data. And here's an example of fine-tuning our like candy Ziploc task on expert data for unzipping a Ziploc full of tools. So in summary, we are proposing this paradigm for crowdsourced data collection in a public space with non-expert users, and sort of focus on this aspect of incentive design to shape the interactions into useful data. Thanks.
Yeah, thanks so much. Hey guys, my name's Ted. I'm here today to present our recent work Steer. The first author, Laura Smith, couldn't make it, but this is with a collaboration with our big team at Google DeepMind. Broadly, we've over the past few months, we've been very inspired by a lot of the successes in large-scale imitation learning that we can see being deployed in static manipulation settings and mobile manipulation or even self-driving. But in a lot of these settings, right, we're roughly operating off of expert demonstration data sets, such as those on the left, of very coarse, skills of the form, place A near B, knock object, pick object, etc., where a lot of these skills are relatively simple and they're collected at the episodic level. But when you compare that with very realistic deployment scenarios, such as pouring something out of a cup and placing it back upright on a table, it's not exactly obvious that everything we want to do in the real world will correspond exactly one-to-one with the definitions that we set a priori in our offline imitation learning teleoperation data set. So if we really think about how humans kind of then operate, yes, for one, humans don't really have such homogeneous training data, but in addition, humans also are able to have a lot of contextual world understanding of what it means to pour or drawing upon past experiences to stitch together previous kind of knowledge into a new test time task. We really like Kahneman's thinking fast and slow, breaking up roughly into a model of how this might work is having like a high level system 2 analytic thinking, and then system 1 low level more reactive motor commands. And we think about what it would take to bring robotics into such a framework. Maybe the limitation is that a lot of our system 1 low-level policies don't really have the flexibility that it takes to really allow a system 2 kind of level reasoning to successfully operate over these low-level system 1 skills. Towards this, we present our method Steer, which, maybe you've seen a very similar diagram before. We take an offline data set of very low level primitives. We relabel with skills that are more easily can be utilized by a high level reasoning policy. We train that multitask policy. And then at test time, we can then synthesize these skills at test time in a very much more natural way. For example, you can use a vision language model to take a test time new scenario to turn that into kind of the skills that your system 1 policy on the left has now learned. And then from that, you can get much more reactive and generalizable behavior. How then do we do this? That's the whole crux of the problem. One kind of thing we identified is that we've seen a lot of progress in like hindsight relabeling, taking existing, very coarse, homogeneous data, relabeling that with denser language annotations so that your language condition policies now have more steerable instruction following skills. What we found is that a particular way to do this is to kind of densely annotate our data set with very dense language captions at much lower temporal horizons, focusing on what actually is important for steerable robot manipulation, such as focusing on aspects such as rotation, grasp approaches, object-centric arm motions. And then for the experiments, what we find is that we do find that qualitatively, we get very good vibes, so to speak, that the low-level policy can now be steered, responding to different ways of basically breaking up behavior modes into specific aspects of like showing exactly how you should do a task, in addition, not just what describing what you should be doing. Quantitatively, we find that this outperforms methods which kind of build off of the same underlying data set, but that do not do this like dense language labeling. We find that, for example, even VLAs, which are trained on internet scale data, don't get this steerability for free. Looking a bit what these rollouts look like, you can see our method on top, being able to utilize the low-level steerable low-level policy to approach the potted plant in a much more natural way, as opposed to, let's say, OpenVLA or RT1, which really don't respond to the affordance of the scene at all. We find that this enables generalizing to new tasks altogether, such as pouring, much better than other kind of hindsight labeling methods, such as goal condition behavior cloning or RT hierarchy, which predicts extremely low-level language motions that aren't necessarily able to be like semantically guided by a VLM. The policy by itself, even without this VLM guiding, can still perform well at individual low-level tasks. Here we show zero-shot generalization to a lot of new objects and configurations. Here's showing an example of a failure mode of why VLAs out of the box may not be enough. In theory, even if they have seen pouring and they've seen understand the semantics of what it means to do these things, those semantics have not been bridged to low-level skills. Finally, the result we wanted to showcase that inspired our project to begin with is to see whether or not VLMs can actually control and orchestrate this more steerable low-level policy. And indeed, we find that both zero-shot and few-shot VLMs like Gemini can control this low-level policy to achieve very complex new tasks. Thanks so much. Our paper and website are there, and hope to see you at the poster.
Hi. How do we build photorealistic simulators that can serve as a data generation pipeline for robotics? Here's an example of our photorealistic rendering video. And here the flying objects are specifically here to convey that these are generated instead of real world. I'm Yishu. I'm here to present SplatSim, zero-shot sim-to-real transfer of RGB manipulation policies using Gaussian splatting on behalf of the authors. So our motivation is policy learning from manipulation from human demonstrations has shown a lot of progress. However, these teleoperation systems, these teleoperation systems are hard to scale because they are quite costly to set up and they require physical robots for each teleoperator. And also, RGB renderings from current simulators look nothing like real world, making RGB-based sim-to-real and out of distribution generalization problem. So our key idea here is to combine the explicit representation of the Gaussian splatting with existing simulator to convert the simulated data into photorealistic data. We rely on the insight that if each rigid body in the scene can be segmented and associated with its body in simulator, we can use the transformation given by the simulator to get a photorealistic trajectory of the simulated trajectory. Here are some examples. These are we generate photorealistic data for 4 manipulation tasks and transfer the policy zero-shot to real world without any data collection in the real world. Now we expand more about our method. The first step is to create a Gaussian splat of the scene with the robot. This is the scan of the thing, and this is the Gaussian splat of the scene. And then we segment the Gaussians belonging to the robot, and we take the means of the Gaussians as a point cloud. And then we find out the transformation between the splat robot frame and the simulated robot frame using ICP. And we find out the segmented means for each link of the robot and then we can apply the transformation. This is how the spatial alignment looks in practice using a cloud compare software. It takes around 15 minutes if you're untrained in the process to find out all the transformation. Have to crop some of the points out. We also show how to segment objects with non-axis aligned links using a KN-based approach. We can also use directly control the splat with a teleoperation tool like Gallo. So our overall pipeline is we first collect expert demonstration in a physical simulator pipe bullet. And in our case, these demonstrations come either from human experts, teleoperation, or through a privileged information-based motion planner. The trajectories from the simulator are then fed to the simulator aligned splat model of the scene and the object. And then we transform the 3D Gaussians to manipulate the static Gaussian splat models to extract photorealistic renderings of the scene at novel joint and object poses, which serves as the RGB state observations for the diffusion policy. Along with these RGB observations, diffusions also take the end effector position and the orientations as the input. And then we train our policy and transfer to real-world zero-shot. Here are some examples of our zero-shot ability. This is the push T task. This is the pick up an apple task. This is put an orange on the plate task. This is a stack block task. And this is a table of our overall success rate. We can see that even based only on synthetic data set, we can achieve 86% of success rate, very comparable with those trained on real world data to show the effectiveness of our method. These are more demonstrations. For more videos and details, please visit our paper and our website. Thank you.
Hi, my name is Joel, and today I will be presenting latent action pre-training from videos. This was joint work with people from KAIST, University of Washington, Microsoft, NVIDIA, and AI2. So where do we get the abundant data? I think that's what everyone is curious about. A lot of people throughout the last few days have hinted towards internet data, video data in the internet being a potential solution. But data in the internet with humans doing a lot of different stuff are widely available, but there's no robot actions, and there exists a human to robotic body gap. We propose LAPA, which aims to mitigate these two problems and train robotic foundation models. Through LAPA, we can take videos such as these with diverse environments and humans manipulating different objects with differing camera viewpoints and learn skills directly to transfer directly to the downstream robotic tasks. So how do we do this? We tackled the problem of having no robot actions by obtaining latent actions from the visual deltas in the videos. We tackled the embodiment gap problem by initializing from a VLM. So LAPA consists of 3 different stages. In the first stage, we train a VQVA where it takes 2 consecutive image frames from video as input and outputs only the second image frame. And we train this with vector quantization, so we get discrete representations. And we only use the tokens or the indexes of the discrete representations for stage 2, where we do supervised fine tuning. And instead of actually predicting ground truth actions, we predict the latent actions represented via action tokens. And stage 3, we assume that we have some trajectories with ground truth action labels collected via tellout, and we fine-tune the VLM. So diving more into a little bit of the detail, first we get the embedding of the 2 image frames from the encoder. And to the decoder, we feed in only the first image and the tokens. So the decoder is forces the latent representations to capture the delta between x1 and x2. And yeah, since it's discretized with the vector quantization, we can have them just as latent tokens, which makes it easier to train LLMs. So yeah, in stage 2, it's the same as other VLA training. We do it, but we just use the latent tokens. In stage 3, we initialize from the VLA, but the VLA cannot do anything in the real world because the action it predicts are latent. So we do the same thing. We have some observation and action pairs, and we fine-tune the VLA, and in this phase, it learns the mapping from the latent to real actions. And we have diverse pre-training and fine-tuning mixtures, but in this talk, because of the time, we want to highlight 2 main experimental setups, the multi-embodiment and human-to-robot transfer. So in the multi-embodiment, we've pre-trained on OpenX. We use the exact same subset used to pre-train OpenVLA. And on fine-tuning, we collect 150 trajectories per task, where there's 3 objects, 1 target, 2 distractors. So it has to do language conditioning, and we test unseen object combinations and unseen instructions. So the first result that I want to highlight is that pre-training helps. So compared to Scratch, LAPA pre-trained on Bridge outperforms, and LAPA pre-trained on OpenX leads to better performance. So this is a good thing because then scaling pre-training data leads to better downstream performance. Second is that LAPA pre-trained OpenX outperforms OpenVLA pre-trained on OpenX, but OpenVLA was pre-trained with actual ground truth actions. So how is this possible? In previous other setups in the work in simulation, actually using the ground truth actions is the upper bound, but in this case, we beat the upper bound. This is the reason why this is possible. The latent actions you can see when we use the decoder of the VQVA to get to the next frame, we can see that the same token combinations, despite the different environment, equates to the same robot action. So the first thing you can see that it goes, the Google robot and the WidowX both goes down and left with the same token representations. This is very different from current VLA training where they discretize based on each data set, which is can't really result in a huge positive transfer. This is analogous to bipair encoding LLM. So we get the atomic tokens in LLMs by going through all the corpus in text. Similarly, we go through all the frames in the videos and try to find the atomic action granularity. So now about the abundant data, now we need to train on human data. So we show results on something which consists of 220K human videos. And the highlight result here is that LAPA pre-trained only on human videos outperforms OpenVLA pre-trained on Bridge. And Bridge is one of the biggest open source data sets. So I think this really highlights the true potential of LAPA. This is just for future work. Because I told you that it captures the atomic action granularity. So it captures any actions between 2 image frames. And something there, the camera moves a little bit. So we see that it also captures the camera movements despite the different environments. So we want to, for future work, we want to extend this to capture more diverse actions, not only embodiment-centric actions, but as well as environment-centric actions to do dynamic tasks. Yeah, thank you for listening. I'm glad to talk more about this in the poster.
All right. Hi, everyone. My name is Lars, and I'm very excited to be presenting our work on diffusion policy optimization on behalf of my awesome collaborators, and especially a big shout out to Alan Wren, who led this project. So recently, there's been a lot of excitement about learning policies with imitation learning from data. And there's been a lot of very, very impressive results, like this shirt hanging task from Aloha Unleashed. This table from the paper, however, caught my attention because as you scale the data, you would expect your policy to improve in performance as well. But here we see we plateau at around 70 to 75%. We think that RL might be a very good way to overcome this limitation of learning from human demonstrations, because you, instead of optimizing maximizing the likelihood of the data, you rather optimize the policy pi to directly maximize the task performance. To do this, you need, and we want to do this with policy gradients. To do this, we need access to the log likelihood of the actions with respect to the policy pi. For a standard Gaussian policy, this is straightforward, as we have access to the likelihood of the action directly. With a diffusion policy, however, this is more complicated, because what we have access to is only the intermediate denoising steps and only the likelihood of each intermediate steps, but not the final action at the very end. So to solve this, we formulate this diffusion MDP, where we model the denoising process itself as a Markov decision process. And then for every time step of the environment, we have such a MDP. And then we can model a whole rollout as a chain of these MDPs. And we get effectively now a two-stage, very long MDP, where at every stage, we have access to the log likelihoods. And as such, and this is how we kind of parameterize the problem for this. And since we now have access to the likelihood at every single step, we can solve this MDP with standard policy gradient methods. And this is how the DPPO works. So we start out by testing DPPO against other standard policy parameterizations, a Gaussian MLP and Gaussian mixture models. And we find that the final performance is greater, much better for the DPPO. And it converges faster at a better sample complexity. And this difference is much bigger when we use learn from pixels directly in RL. And we want to highlight this task in particular because this is a very long horizon challenging task from the RoboMimic task suite, where DPPO can achieve over 90% success rate. And to our knowledge, previous methods only achieved roughly 50%. And considering that this is like here we have an effective action space of 112 dimensional actions. We use sparse rewards and only get the reward at the very end for task completion. And we use no regularization like BC loss. We still can achieve these results, and it shows that DPPO is a very powerful method to solve long horizon manipulation tasks. We also tested out on this multi-stage manipulation task requiring high precision from Furniture Bench. And again, find very, very strong improvements over the pre-trained policy, and especially here on the roundtable task, we go from 1% pre-training performance up to 86% success rates. And maybe more importantly, the qualitative behavior we get is much smoother and more natural with DPPO compared to the standard Gaussian MLP parameterization. And this property also provides for much stronger sim-to-real transfer, because on the left here, you see the DPPO policy is very smooth and nice, and we have very consistent performance between sim and real. On the right side, we see the Gaussian MLP, though working pretty well in sim, has very erratic behavior in real and causes robot errors, and as such doesn't transfer at all. So then we do some deeper exploration and find the two properties that we think causes DPPO to work so well. So here we consider this very simple avoid environment. And we have these three settings with different modes, depending on what expert data we pre-train the models on. And then, as we've pre-trained the same models, the DPPO, the Gaussian MLP, and the Gaussian mixture model. And in the beginning of the fine-tuning phase, we add exploration noise. And the resulting policies we plot here. And then we consider what they look like. And we see for the DPPO, the resulting exploration trajectories cover the expert data well and stays close despite having noise added to them. And compared to the Gaussian MLP, the exploration is much less structured and ending up being all over the space. And this property of staying close to the expert data, but still covering it, is what we call the on-manifold exploration. And yeah, and this is what we think might speed up the training and also regularize the behavior to make sure we're staying close to the expert data. Yeah, providing more natural and smooth fine-tuned behavior. We also find that DPPO is more robust to OOD initializations and more robust to action perturbations throughout the episode. And yeah, and this obviously helps with deployment, but also allows for more domain randomization at training time, which also helps with sim-to-real transfer. So yeah, in conclusion, we present DPPO, a method to fine-tune a pre-trained diffusion model with policy gradients directly. And the takeaways are pre-trained diffusion models can be brittle, but it provides a very good base for fine-tuning. We find that DPPO can effectively leverage the wide coverage that the diffusion policy provides for efficient online exploration. And the structured exploration leads to more natural behavior after fine-tuning. And now we're very excited to take this even further to buy, for example, training on bigger data sets of multitask data, and then yeah, doing fine-tuning in, of course, the simulator, but also in the real world, or using generative simulations and similar. So yeah, thank you so much.
Thank you so much. Yeah, sorry about the mess. Okay, so this is Yi from Stanford, and today I'm happy to introduce you ManiWAV, learning robot manipulation from in-the-wild audiovisual data. So audio signals reveals a lot of rich information about the interaction and object properties. This is a video of me holding this handheld gripper interacting with a lot of objects. And we can hear that the audio signal contains a lot of information about the interactions. So we asked the question, how can we leverage audio feedback for context-rich manipulation skills? So we built on top of the UMI gripper by Chi et al. And embed a contact microphone inside the gripper finger. And for each demonstration, the audio data is recorded synchronously with the vision data through the external mic port of the GoPro camera. And here are some advantages of contact microphone. First of all, it's cheap. It's only $10 off the shelf from Amazon. It's robust. I can only use one microphone to conduct my entire experiments. And it's insensitive to background noises due to the nature of the piezoelectric material that only pick up signals transmitted through solid objects. And it's easy to record and store with vision data into MP4 files. However, here's the challenge. So let's hear a recording of the human collected demonstration. And this is a recording of the robot deployment. So we can hear that the robot motor noises and other robot interaction noises generated during test time is causing an audio domain gap. To address this, we propose an audio data augmentation technique. We randomly sample noises from a recorded dataset of robot noises and the ESC50 audio dataset and overlay it to the original audio signal. And the final sensory motor learning model taking fisheye images and the log mouse spectrogram converted from the augmented audio. And the visual features and audio features are fused through a transformer encoder and finally passed through a diffusion policy to generate the robot actions. And we systematically evaluate our method on 4 context-rich manipulation tasks. And today I'll dive into 3 of the tasks. The first one, the robot is supposed to wipe the shape off from the whiteboard. Now the challenge of the task is to infer the contact between the eraser of the board while following the shape. And we can see that by leveraging audio signals, our method is able to correctly infer the contact between the eraser and the whiteboard. And the policy is also able to generalize to unseen table heights, unseen shapes, such as a star that's not in the training data set, and also to a different eraser with a slightly different wiping material. And here are some results from the baselines. I think I don't have time to delve deeper, but it's worth noting that for the vision-only baseline, the policy will tend to float above the whiteboard, as the contact between the eraser and the whiteboard is hard to be inferred from only the image coming from the wrist mount camera. And here's a bagel flipping task. We can find that our method is able to correctly insert the spatula between the bagel and the pen and then flip when the bagel is in contact with the edge of the pen. And the method is also able to generalize to unseen table height, and it's also robust against background noises due to the nature of the contact microphone. So one of our key findings is that by incorporating contact audio as an additional source of information improves the robustness and generalizability of the policy. To delve deeper into this finding, we actually visualized the attention map of the VIT encoder used in our method and found that a policy trained with both vision and audio attend more to the task relevant regions, comparing to a policy trained with only vision data attends more to the background features, such as the edges of the whiteboard or the room background. And another finding we have is that noise augmentation is an effective strategy to bridge the audio domain gap between human collected data and robot deployment data, as it improved performance by 50% on the wiping task comparing to a baseline with no noise augmentation. And here's one of the interesting experiments I would like to show is that we found that the contact audio is sensitive enough to different surface materials. So the task here is that there are Velcro tapes that are with different materials that can either be loop or hook, and the tapes are randomly placed on the right, and then on the left there is a loop material underneath the wires. So the task is basically to find the correct tape that can attach to the loop tape underneath the wires. So we can clearly see that there's a difference in terms of surface materials that could guide the policy to choose the correct tape. And finally, we conduct in the wild experiment where we will use the handheld gripper to collect diverse in the wild demonstrations of the bagel flipping task. And we find that our policy trained on diverse in the wild demonstrations can zero-shot generalize to this unseen environment, whereas a policy trained with data collected only in the lab tends to drift away from the object. And so here are the quantitative results and show that the in the wild demonstrations enable generalization to unseen in the wild environments. Yeah, if you're interested, feel free to check out the project website. And yeah, thank you all.